Are these AI systems something that can be fooled? And this is kind of what we came up with. These were adversarial patterns that you could think of as almost like AI camouflage, or kind of like, I actually like to think about it as like catnip for AI. The AI just goes crazy for these patterns and ignores everything else. In 1950, Alan Turing asked a deceptively simple question: can machines think? And it seems appropriate to start here in an event that is organized by an institution that bears his name and in his country. That question really spawned an entire field. And 6 years after Alan Turing asked it, a group of intrepid and pioneering researchers decided to kind of stop asking and start building. And I have to say, there must have been something in the air that summer of 1956, because when this group of intrepid researchers got together, they didn't just kind of step into the unknown. They really just sprinted into it. And just to give you a sense of what was going on at the time when these folks came together, they were kind of against the backdrop of Cold War era competition. They were bound by severe technological constraints. And they made up for it with this kind of unbridled pioneering optimism. They saw this challenge of imbuing machines with the ability to think and reason and even learn, and they saw a solvable puzzle. And it really kind of sparked this era of beautiful hubris for this particular field. And to give you a sense of the kind of audacious optimism that this group had, here's a particular example of one of them. His name was Marvin Minsky. This was back at MIT. And he proposed to kind of unravel the evolutionary mystery of the human visual system. My ability in this case, I'm looking at the room over here, and I'm able to read emotions, perceive the 3D structure of the scene, and kind of make sense of it all. He proposed to solve that as a summer project. I kid you not. And here you have it. What we now know to be a kind of multi-billion-dollar, decades-long scientific field, Marvin Minsky basically gave it as a summer research project to his interns. Now, of course, we all know things weren't quite as simple. September rolled around, and there was no quick solutions. Now, if you fast forward to about 38 years later, that's when I had the opportunity to meet with Minsky and work with him. And by that point, this idea of any kind of quick fixes or solutions to this challenge was kind of long gone in a distant memory. This kind of breezy summer project had actually turned into a decades-long just grind of incremental and slow improvements. But you know what? I was kind of the new entrant. I was a fresh graduate student. I had all the energy in the world. He was passing the torch to me. So I was, ready to charge this thing. And one of the first projects I had, as a graduate student was this thing called the DARPA Grand Challenge. And the premise was certainly grand. The idea was to, gather all the scientists having to do with artificial intelligence and robotics and kind of bring them together to see if we could complete this autonomous vehicle driving course. The reality, though, is at least my car kind of boldly drove for about 30 seconds before decidedly slamming into one of these barriers and obviously not completing the course. Luckily, at least for me, I was in good company. I wasn't the only one in this situation. And that year, not a single team managed to complete the course. So you see, I pretty quickly, despite that sense of optimism that I brought into this, I pretty quickly settled into realizing that this is what life in AI research looks like, and where you would work very hard in the lab only to then deploy something in the real world and essentially watch it fail miserably. So this is what my life felt like right there. And you know what? I was perfectly content to accept that. I really wasn't prepared to see any major leaps in my lifetime. That's what science is. We all kind of chip away at a problem and we pass it on to the next generation. In the summer of 2012, something really interesting happened. It was the confluence of two things. On the one hand, we saw this kind of appearance of these large-scale labeled data sets. And the key word there is labeled. What it would take is individual people manually labeling these images one by one for the purpose of training AI. ImageNet, which is what you're seeing over here, took about 50,000 people to put together. I was one of them as a graduate student, just sitting there, one image at a time, labeling it, and the things that you do for science, I guess. The second thing that happened had to do with hardware, specifically these graphical processing units. These things were originally made for kind of hardcore gamers or graphics enthusiasts. And it turns out that this particular hardware was especially well equipped to conduct the kind of mathematical computations that we needed to accelerate these neural networks. So the confluence of both of these things created this kind of Cambrian explosion, if you will, of sudden progress. We saw applications that actually worked, kind of. We saw applications in computer vision and speech recognition. And as someone who was just accustomed to failure after failure, suddenly this kind of glimmer of hope was just amazing. And the scale of these systems was just on a completely different level of anything that we'd seen before. When I say about the ability of training on the entirety of the kind of the human corpus, written corpus, I really do mean it. At some point, we almost started running out of training data. So it was anything anyone's ever written that's out there. It started being to the point where we were training on old Aramaic and like old scrolls that had been discovered in Egypt because we were running out of training data. And the scale to train these things is just astounding. If you have a computer that's able to do 1 billion computations per second, if you think about what it would take to train one of these systems, it's not days or months. With a computer of that capacity, it would take more than 100,000 years. And here's the part that changes the timeline math. These systems are now accelerating their own development. It's kind of AI for improving AI itself, where AI is writing the code that's going to train the next system. And the AI is using its own ability to discover the architectural improvements that need to be discovered for the next generation of systems. And here's the part that concerns me. AI had its transformer moment, if you will, but our institutions have not. The policies, the procurement processes, oversight mechanisms, they were all put together in a world where we could see technology develop in a relatively predictable way. And now it seems like we've advanced to a world where AI kind of leapt forward, but our ability to see it clearly really has not. And here's why that matters. Kind of the decisions that are being made right now in terms of how AI is developed, how is it evaluated, where does it get integrated across critical systems that we all rely on? Those are all decisions that are becoming scaffolding. And scaffolding is really hard to swap out once you start building on top of it. So what I want to do today is talk to you about 6 different areas where I see pressure mounting. We're in this window where scaffolding is starting to get created, and it seems evident that there's certain pressures that are starting to happen, and it's not uniform. It's not across every organization, it's not across every domain. But also what I want to try to convince you is that these are not necessarily separate problems at kind of different layers across different domains. They're kind of a single condition expressing itself in 6 different ways. The first pressure point is one that I've kind of lived with for a long time, and so has Chris and others at the Turing Institute. It's this intersection of AI and cybersecurity. The same capabilities that can defend a system can attack it. And this is not necessarily new in the world of cybersecurity. Cyber has always been this kind of dual-use technology. It has 2 sides of the coin. A lot of the things that help defenders can also help attackers. But as we'll see in a bit, some of the recent progress in AI is really changing the nature of the game in this particular domain. And what I found was actually, it really surprised me, and it really surprised the entire team. What we found was that these models were incredibly capable of looking at large-scale code bases and finding specific vulnerabilities that in many cases had been lying there dormant for decades and hadn't been discovered by people. And the scale at which they were able to do this is something that just could not be matched by any individual or even team of people. And up until now, this world of cybersecurity has been very much kind of like this human versus human cat and mouse game. You could almost think about it like a kind of a game of chess, where you're playing and then you have an adversary. But this kind of analogy is under serious pressure right now. Because when you have a machine that's able to explore vast spaces, more than any one human can hold in their head, and explore strategies throughout this combinatorial explosion of possibilities, it really doesn't become a kind of a human versus human player. Now you really change the nature of the game. The same capability stands in both sides of the coin. It's able to assist with both the attackers and the defenders. In this particular case, though, there's a slight advantage to the attackers because they only need to succeed once, whereas defenders need to succeed every single time. The second pressure point that I want to talk about is having to do with what capability happens once it's been developed. You see, when you're developing these frontier AI systems, they don't just stay there where they were developed. In many cases, they're being deployed across different applications. In some cases, the frontier models are just uploaded to the internet as part of a set of weight files up in the internet. But they also proliferate in new ways that are actually not even talked about much or don't make really the news. There's a whole new area having to do with model distillation, which is how you're able to extract capabilities from a frontier model just by observing how it interacts. We're moving into the space of high-stakes applications of AI. This is very different from that video I showed you of Jan LeCun, recognizing digits that were written by hand. We're really moving in a completely different space, where the uplift is incredibly exciting, but in the wrong hands, it could also accelerate capabilities that we've been trying to contain for 50 years. And here's the part that makes this not just kind of a paradox. Really, the containment frameworks that we've inherited up until now for technologies were built for kind of a world of atoms, right? Physical materials, things that I could almost see going across borders. Nuclear containment, as an example, kind of worked. It's not perfect, but I guess it somewhat worked. But there's another set of examples. One example is in the 90s, we tried to contain knowledge of cryptographic algorithms. How do you encrypt material? And that failed miserably. And the reason it failed is because once math is out there, some particular math algorithm, it's hard to contain that knowledge. So AI is probably closer to cryptography than it is to nuclear. In fact, we have this kind of idea of tracking the proliferation of a particular AI algorithm, and you would see it light up. There's all of this activity having to do with people who are taking initial models and distilling in part from these, and they proliferate. So the third pressure point I want to talk about has to do with another area that is usually not talked about that much in the news, and that's counter AI. It turns out you could take an image like on the left, perturb it ever so slightly, and it makes the AI completely confused. And that first you might think that's just kind of a peculiar property, but it turns out that that in of itself can also be kind of exploited, right? So if you think of something like a stop sign and you wanted something to not recognize it as a stop sign, what we started calling it were adversarial patterns. These are particular patterns in the image that were explicitly crafted to confuse the AI. So as we started moving into this world of kind of high stakes applications of AI, whether it be financial sector, defense, health, a lot of people started really being concerned about the fact if it's that easy for me to essentially fool an AI system, we really ought to think twice about how we deploy these systems. So back then I was actually just working in my office and I got this knock on my office door. And I'll never forget it. I mean, I looked back at the office and suddenly there was this stern Marine colonel staring at me with exactly that stare. So he said, in his own way, which I cannot mimic, it's like, I heard these AI systems are weak and they can be fooled. It was upon me to say, this is very much kind of a research space. This is kind of an academic kind of exercise at this point. But regardless, people were very concerned about this at the time. And then suddenly I was out in the desert in Nevada, in the middle of nowhere, an AI researcher never imagined, like close to Area 52 and all this stuff. And we were doing, what we were calling counter AI kind of research, thinking about, are these AI systems something that can be fooled? Again, very hypothetical, very researchy. And this is kind of what we came up with. These were adversarial patterns that you could think of as almost like AI camouflage, or kind of like, I actually like to think about it as like catnip for AI. The AI just goes crazy for these patterns and ignores everything else. So we did this kind of test, as a maybe responsible way of covering our bases in research. It was interesting to be part of, but nonetheless, very much a kind of looking into the future of what we should be concerned about. This is kind of what it looked like. You have these patterns, and they suddenly are able to completely confuse the AI system into thinking things that it's kind of hallucinating. Now, fast forward to today, which was before a kind of a hypothetical that'll never happen. Look at this image and look very closely. These particular patterns that you're seeing in the case of tires on this Russian bomber plane are not accidental. They're actually deliberately placed there to try to fool autonomous drone systems. So we went from this idea of a very kind of hypothetical, maybe someday people will be attacking AI systems, to now this is kind of the quiet reality. It doesn't get reported a lot in the news. But we're in this world now where AI is integrated into critical environments, and there's this cat and mouse game that's different from cyber, but similar. Now it's opened up a whole new dimension, this AI against counter AI. So the fourth pressure point, it has to do with monoculture. For a lot of us, we've kind of made this big bet on AI, and AI is essentially one big bet on a single model architecture. So if you pick any country, and I'll pick the US just for the sake of it, and you look at the number of frontier companies, there's usually less than you could count them all with one hand. And they're all very secretive about what they're doing, rightfully so. There's a lot riding on the line financially. But the open secret is everyone's using the same model architecture, which is the transformer that we talked about before. So in some sense, we've kind of made these architectures critical infrastructure without actually having a conversation about it. And also without imbuing these models with the kind of critical infrastructure protection that they warrant. When we have them embedded in national security systems, critical infrastructure systems, consequential decisions are being made, and it just kind of happened. So the reality is that we've kind of been here before in the kind of biological sense, and we know that when we have monocultures, failure doesn't just happen gracefully; it happens all at once. So this is one that concerns me, in the sense that right now we have a lot riding on a single type of AI, a specific type of architecture, and a correlated set of failures is not too hard to see. So pressure point 5 has to do with asymmetry and how we react to what's coming at us. And I see this even more now that I'm working with a lot of kind of government and kind of civil society. And it's really kind of become a pattern. I don't know if you guys saw recently, Anthropic had a model called Mythos that they were concerned about from a kind of cybersecurity perspective. And this was kind of a perfect example of it. I saw everyone scramble to try to figure out, how do we even know if this is something we should be worried about? So on the one hand, having lived at these frontier labs, they're so well equipped. We have internal red teams. We have the hardware. We have the compute. They have the know-how. But there's this big gap between every other organization that needs to be able to contextualize and try to assimilate how does this affect me and what we need to do. And that delta, that difference between what's happening in the frontier level and then also every other organization that's going to have to react to this is vast at the moment. And here's kind of why it matters. You have this kind of vast middle. You have organizations like that water treatment plant that I talked about. And for many of these organizations, what they're staring at is a big black box in the middle. That initially, they're able to understand a lot of their system. And as we integrate more AI, they have to take it on trust. The sixth pressure point is something that I think you are all aware of, but I needed to name. And there is significant pressure between, obviously, it's been a story that's been told before, which is that technology advances much faster than regulation and kind of policy can keep up with it. But maybe kind of a nuance that I think is important to appreciate is that policy is being set right now, and usually policy sticks around much longer than you intend it to. So at the moment, and right now, as we speak, policy is being written for, I think, systems that might not even be around. The stuff is moving so quick. And it's become more than kind of an inconvenience. At this point, it's really become, I think it's an actual pressure point. So we saw 6 pressure points. We talked about dual use, proliferation, capacity asymmetry, counter AI, monoculture, policy velocity. We've gone through a journey. And you might be thinking, okay, which one of these do I care about? What is this one? Okay, maybe this one is important to me or not. But I want to make the case that what you just saw was essentially each and every one of these was essentially a differential going in the wrong way. Right? Defense behind offense, governance behind capability, comprehension behind deployment. What they all share is essentially a structure. Each and every single one of them is kind of a gap between two things that are adapting, and one of them is ahead of the other. So what is resilience in this case? So resilience is really this kind of capacity to hold a margin. How fast you're able to adapt while things are adapting around you. You either hold it or it closes. And this margin kind of compounds. One cycle of difference this year can become 2 the next. And the capacity to kind of hold that margin requires dedicated work. And the other thing is that there is no outside. The institutions in this room, the organizations that you work with, the frontier labs that are developing this technology, no one is looking at this from some kind of safe space. We're all inside of it. Every decision that gets made or doesn't get made and is deferred is shaping that margin. So that kind of window of opportunity, that margin is here now and in this room. And this kind of brings us back to Turing and where we all started. Turing's genius was really not about prediction. It wasn't about control. It was about identifying the limits of what is even knowable and then building anyways. His work on computability was an act of profound intellectual humility. He asked not, how do I solve this, but what is solvable at all? And within those limits, he moved out in an incredibly decisive way. So the honest question right now at this frontier that we're all facing is probably something that Turing would have asked himself. It's not, how do we stay safe? How do we contain? It's whether we can become adaptive enough to be able to operate at a frontier that we can't fully verify. And no single institution is going to answer that themselves, no single nation. It's being answered in bits and pieces by everyone who is in this dynamic, including you here in the room, whether we intend to or not. So Turing opened with a question, can machines think? And I want to close with its companion. Can we think well enough to govern machines that think? Not predict, not contain. Can we think well enough? That's really the work. That's what resilience looks like at this moment, not armor, not certainty. It's the capacity to keep learning, to keep adapting, to keep widening that margin within a window that might not always stay open. With that, I thank you.